Hello, and welcome to our discussion of the start of section 1.5.1 on nth order linear, constant coefficient, homogeneous ODEs. So such differential equations can be written in the following form: constant an times the nth derivative on f plus constant an minus 1 times the n minus first derivative on f, then descending downwards in derivatives to adding a constant a1 times first derivative on f plus a constant a0 on f, and this is a homogeneous equation, so the right-hand side should be 0. And we will compress this in this video and in the notes as a on f is the sum from k equals 0 to n of the coefficient ak times the kth derivative on f, and that has to be 0 because this is a homogeneous ODE. And we're allowing in this discussion a coefficient an on the nth derivative, but we require that an should be non-zero, because otherwise this wouldn't be an nth order linear equation. Now, how do we solve this? Well, we got pretty good at solving second order linear equations, in particular second order linear homogeneous equations. So let's do what worked before. We'll guess f of x is equal to e to the lambda x for some number lambda, where lambda may be complex, and then we'll try to figure out what lambda is. So first we need to remember what the chain rule says. If I differentiate e to the lambda x k times, I get back lambda to the k times e to the lambda x. So I do that for each of the terms in my nth order equation, the nth derivative, the n minus first, all the way down to the first derivative, and then the term a0f. And I pop out from a on f equals 0 the following equation: an times lambda to the power n plus an minus 1 times lambda to the n minus 1 plus all the way down to a1 times lambda plus a0. That whole quantity, that whole polynomial in lambda, times e to the lambda x is equal to 0. So I can solve my ODE a on f equals 0 with the guess f of x equals e to the lambda x, if and only if I have this relation polynomial in lambda times e to the lambda x equals 0. And of course, e to the lambda x is never 0, so I just divide that off, and I really want the polynomial part to be equal to 0. And as before, I'm going to call this polynomial chi sub a of lambda, and that is the characteristic polynomial for my differential equation. And the only difference between this characteristic polynomial and the one we saw with second order equations is that now I have an arbitrary nth order or nth degree polynomial, so it's going to require a little more work to solve. So our goal is to solve the polynomial equation an times lambda to the n plus an minus 1 times lambda to the n minus 1 plus all the way down through a1 times lambda plus a0 equals 0. And this is always possible because of the fundamental theorem of algebra, which we will now review. We will, rather later in the course, prove the fundamental theorem of algebra using complex analytic techniques. The result is that the polynomial chi a, this nth degree polynomial, has n roots counting multiplicity. So what does that mean? First, I can find a number r, with r being between 1 and n, and I can find r distinct numbers, lambda 1, lambda 2, up through lambda r, which may be complex, such that if I plug those numbers lambda k into chi a, I get 0. That is, the characteristic polynomial chi a, evaluated at lambda k, is 0 for k equals 1 through r. Moreover, I get positive integers m1, m2 through mr. So these positive integers are associated with the r numbers lambda 1, lambda 2 through lambda r. And these positive integers, m1, m2 through mr, satisfy first the sum m1 plus m2 plus all the way up through mr is equal to n. So these numbers mk add up to n. And I get the final factorization. Chi a on lambda is equal to an times the factor lambda minus lambda 1 to the power m1 times the factor lambda minus lambda 2 to the power m2 times all the way up through the factor lambda minus lambda r to the power mr. And if you like, I can compress that in the product notation, an times the product k equals 1 through r of the factors lambda minus lambda k raised to the power mk. So the fundamental theorem of algebra tells me that I can solve the characteristic equation, and I get a bunch of roots, r roots, maybe r is equal to 1, and I just have a really repeated root, maybe r is equal to n, and I have n distinct roots, and the roots compared with multiplicities, which are positive integers, so that I have this factorization in terms of the lambda k. So the long and the short of it is, it looks like the functions e to the lambda 1x, e to the lambda 2x, all through e to the lambda rx, always solve my nth order equation a on f equals 0. There's just one catch. What happens if my index r is strictly less than n, and the characteristic polynomial chi-a does not have n distinct solutions? We saw this in the first week with the repeated real root in the second order characteristic polynomial. So we just do what we did before. We add powers of x. So let's say that lambda k is a root of chi-a, and it has multiplicity mk. Then I'm going to construct mk functions below. My first function will be e to the lambda kx. My second function will be x e to the lambda kx. My third function will be x squared e to the lambda kx. And then my mkth function will be x to the power mk minus 1 e to the lambda kx. So don't be confused with the counting. The last power of x is mk minus 1, but I start with this e to the lambda kx, and that has no power of x in front of it. I claim all these mk functions solve af equals 0. And they are all linearly independent. So that's what I do for one lambda k. But for each of the lambda k's, allowing for multiplicities greater than 1, I'm going to cook up n functions as below. The following n functions all solve af equals 0, and they are all linearly independent in the vector space of n times differentiable functions on R, Cn of R. So here are my n functions: e to the lambda 1x, x e to the lambda 1x, through x to the power m1 minus 1 e to the lambda 1x. Those are m1 functions. Then I get another m2 functions, e to the lambda 2x, x e to the lambda 2x, all the way through x to the power m2 minus 1 e to the lambda 2x. And I keep doing this until I get up to lambda r, and then I'll have mr functions, e to the lambda rx, x e to the lambda rx, all the way up through x to the power mr minus 1 e to the lambda rx. And remember the property of the multiplicities, m1 plus m2 all the way up through mr is equal to n, so I have n functions here. And these n functions form a fundamental solution set for the differential operator A, just like in the second order case. If I call these n functions j1 through jn, just to call them something succinct, first, the set j1 through jn is linearly independent, and this set spans the kernel of A, in the sense that if af equals 0, then I must be able to write f of x equals the sum from k equals 1 to n of ck on jk of x for some constants ck. So any solution to the homogeneous problem, a on f equals 0, is given by a linear combination of these n functions from the previous slide. And this is what I call theorem 1.5.1 in the notes. So now let us use this theorem to find a fundamental solution set for the differential operator a on f is the fourth derivative on f minus 16f. The first thing we do is find the characteristic polynomial. This is lambda to the 4 minus 16. So of course we want to find roots of the characteristic polynomial, and we factor it. This factors first as lambda squared plus 4 times lambda squared minus 4. And that factors as lambda squared plus 4 times lambda plus 2 times lambda minus 2. So by inspection, I see the roots are plus or minus 2 and plus or minus 2i. And so one fundamental solution set is to take e to the 2x, e to the minus 2x, e to the 2yx, and e to the minus 2yx. And these four functions are linearly independent, and they span the kernel of A. You'll note that I had four roots to a degree 4 equation, so all four roots had multiplicity 1. I didn't have to put any extra factors of x on my functions here. Now, the differential equation here, fourth derivative on f minus 16f, has all real coefficients, and so it's always nice, though not necessarily required, to be able to come up with a real-valued fundamental solution set. And I can do that just by taking the real and imaginary parts of my different functions here. And I find that another fundamental solution set is e to the 2x, e to the minus 2x as before, but now in place of the complex exponentials, cosine of 2x and sine of 2x. And so any solution to fourth derivative on f minus 16f equals 0 looks like a linear combination of the functions in either of these fundamental solution sets.